Hello and welcome to the next major module in our sequence. Now, well, so far we've been dealing with the easy stuff. That is, learning about the language and how it corresponds to specific hardware constructs. Now we're going to get into the process of designing a complex digital system that is something consisting of more than just a handful of gates or flip-flops, or consisting more of one module in Verilog. And we're going to have two modules actually related to this. One will be this one, how to design complex digital systems. And the next one will be a short one on how to partition a complex system into a set of modules. Now, this is actually going to be a little bit of an art rather than a science, though I'm going to try to reduce it to a process at least as best I can. But this is an aspect where really being able to think globally as an engineer in terms of how to best structure and design, how to best approach it, and really understand what logic can and can't do for you comes to the fore. But we're going to try to tackle this in a methodological fashion as best we can. What I'm going to do is start off by describing the steps in an organized design approach that lead to an overall efficient design. Then I'm going to get into a general discussion of how to maximize performance or efficiency. By efficiency, I generally mean performance per unit area, which is maximized by having your design have as much of microparallelism operating at the same time as possible. Then I'll go into an example that actually illustrates a lot of these general points and shows how creative thinking can lead to a very efficient design. Then I'm going to have a short section on C to Verilog, and I want to emphasize this section is short. This is not how to write, how to produce good RTL. I'm really going to try to illustrate how if you're completely stuck and you have an algorithm written in C, you can use this to get some idea at least how to approach the hardware. Then I also have a brief section on minimizing power design. We'll return to that a lot more later in a whole separate section on low power design. This relates to the references here, including the motion estimator, which is the example here and comes from the book that's referenced at the bottom here. Okay, so my objectives are to try to give you a structured approach to partitioning, to start introducing you to the art of complex design, and a practice on an example, then leading into the C to Verilog and low power. So I want to remind you of our course mantras. So please recite after me. One clock, one edge, flip-flops only. And remember by this I mean within one module. All modern designs actually have multiple clocks. The second, most important mantra, design before coding. If you do this, you won't end up with a bunch of garbage code that doesn't actually correspond to logic. Code that corresponds to logic is very highly constrained. And we've seen this in the last few sets of notes in Verilog 1 and Verilog 2. Behavior implies function is the reverse process. Given a piece of Verilog, how it behaves specifies to you the function you're implementing. And this is well illustrated in the blocking versus non-blocking examples. And now we're going to deal with the fourth and final mantra. Clearly separate control and data path. This greatly simplifies how to approach a complex design. But I'm going to tell you, do the data path first. Without this, what I tend to see in students' designs is a mishmash of control and data path. This does that, then it does that, then it does that, and goes around like that. And it gets very confusing very fast. So now let's get into the steps. These are the steps I'm going to suggest you take in approaching a large design. The first step is to determine what you're going to do. That is, determine the algorithm. And in fact, in any modern design, this is coded in a high-level language. C++, System C, MATLAB if appropriate, and so on. However, unfortunately, the algorithm that's best suited for sequential code, such as C, is not necessarily the same algorithm that's best suited for hardware implementation. And this might require a bit of thought and frankly a bit of research into possible alternative algorithms that are out there. looking through papers, looking through books on algorithms and so on. Because in particular, the key distinction is the sequential code executes on a serial processor. In contrast, in your hardware, the native parallelism of the hardware can leads you. You want to be able to exploit that, and that can lead you to quite a different set of steps to undertake. The second step is to explore the design. This is a little bit of top-down and bottom-up, so we've already done a bit of top-down in step 1. So this might be a little more bottom-up. What are the things that the data path needs to do? What are the micro-operations that have to be performed on the data path? What is the critical path likely to be? And how fast might it be? In many designs, you have to meet a fixed performance. In order to do this, you need to know how fast the critical path is, so you can then in turn how much parallelism you might need in order to meet that fixed performance. We'll see this in the example we'll deal with soon. So these are the types of things you'll do early in the design process. Next is design the data path. Design the data path first. The data path comes from the micro operations that you have to perform in order to meet the sequence of operations needed for the algorithm. So you organize the data path to perform those micro operations in an efficient way while maximizing your use of resources while minimizing your area. This is where the art comes in. It's not so much art, but it's creative thinking as an engineering with an intimate understanding of what digital design is about. And now say do this down to the register transfer level. I'm not saying here write code, remember design before coding. What I'm saying is you explicitly have to identify and name all your registers, then think about the combinational logic that's between them. Then, while you're doing this, you have to think hardware while doing this design and try to be efficient about this. How do you make, particularly what you're thinking about here, is how do you your ideal is all your logic is operating on each and every clock cycle. That is actually your ideal that you're trying to strive for here. One thing I've shown in the examples I've given you, particularly in the pencast examples, is you actually want to draw a timing diagram by hand. This allows you to catch a lot of potential bugs before coding, and the last step in defining the data path is convert this to code. And if you understand how to code, this is almost mechanical. Different blocks of logic become different code constructs. You might have to think a little bit how to make the code capture an efficient design. I've given examples before of how to do this. But the data path is going to be translated into code. And in doing this, you try to make sure you prevent unintended latches, wired or logic, and timing arcs. Then, after you've coded the data path, you identify the control lines and status lines brought out from the data path. For example, oftentimes you'll have muxes in the data path with control lines going to them. These control lines will eventually come from the controller. So they're an example. You might have status lines coming from data paths such as overflow, zero, and so on. Now, if you've done this well, the rest of this is actually relatively straightforward. I won't say easy, but straightforward. Because the next step is to determine the control approach you need. And we'll talk about the standard different control approaches. There's not many in a moment. Then you go and implement the controller. All it's really doing is toggling the control lines in a specified sequence so that the correct sequence of micro operations can be performed on the design. In addition, you need to think about reset and make sure it's properly applied to your design. So let's talk about the common different control strategies. And in fact, these are all of them for the purposes of class on these 2 pages. The standard control strategies tend to be either to implement a counter or a finite state machine. The distinction is really quite simple. A counter goes through a sequence of states. Once it starts the count, it might stay in one state initially while it's waiting to start the count, and then circles back around to that initial state. In contrast, a finite state machine has an equivalent finite state diagram that includes choices in it. There are decisions that are made as you go along. Thus, the distinction in the logic tends to be straightforward. In a finite state machine, we had a complex piece of logic, a combinational logic, that calculated the next state based on the current state and on those inputs. In contrast, the counter, the next state logic is quite simple. You just add 1 to the current state. So in reality, these are fairly similar, but a counter is often explicitly designed using the templates I give you in this class when it is called for. Finite state machine, of course, you're going to have these complex decision trees with alternative next states, and that leads to the use of the more or merely template that I gave you in a previous set of notes. One variation of a finite state machine is when it's used to control a pipeline. You might recall in a pipeline, you break the logic into different stages. I gave the example of the comparator. In each stage, you're doing a different set of steps. What you do is simply pipeline the finite state machine to match to this. So for example, if this was your original finite state machine without the dashed lines here for the original design, then what you're doing is instead of having a finite state machine like such as shown here with its feedback, what you're doing is feeding forward the next state to the next piece of logic. So if you look at the registers here, the stage 1 control logic determines the state that is the input to the stage 2 control logic. So for example here, in the stage 1 control logic, you'd normally determine the next state going to the state vector. Instead, that's going to the state controlling the stage 2 logic, depending on which branch you take here. Similarly, from that, the stage 3 control logic has a separate state register, I call it here state S2, which is the next state coming out of stage 2 being transferred to stage 3. So by doing this, you're essentially overlapping, you're pipelining, so you're permitting a logic operation, a set of logic to go through these 3 stages in a wave and have 3 waves in progress at the same time, which improves the efficiency of the logic. By implementing the state logic like this, you are allowing this overlap to be explicitly captured while permitting alternative control line sets for each stage of the data path. This is fairly, you might have to think about this a little bit before applying it to a design. I'll give an example in a later sub element that supports this particular set of notes. I will remind you about the importance of reset. It's a global signal. It's an input to your design. You cannot modify it. It is used to get the design into a known state, either on power up or if it's gotten into a state that's not giving the correct behavior. It allows you to get back into a state from which you can get correct behavior. It must be distributed to all finite state machines, most of the counters that are within your controller at least, and selected status registers, which might be in your controller or might be in your data path, typically more in your data path. I do want to point out something here as you're starting to implement larger designs. Often the reset signal will lead to a high fan out warning in synthesis. And this is actually okay because in our design we can actually have reset asserted for many clock cycles. It can be a slow signal with a high fan out, And it has a high fan out because it's going to many flip-flops within your design. So you'll get this warning in synthesis, and it's actually okay. In fact, reset, solve, and distribute using a tree, much like the clock trees we talked about in the timing notes. So now we've identified the major steps, I want to remind you about issues related to achieving efficiency. You need to exploit the implicit parallelism that hardware can perform. The huge difference between an ASIC and code running on a sequential processor is this parallelism that's available in the ASIC. The ASIC can be doing thousands, if not millions of things every clock cycle. Whereas in a simple CPU, it's only doing one thing per clock cycle. This is a huge difference that leads to the much larger performance of an ASIC over the same algorithm running on a sequential processor. Often at the high level, what you must be thinking about, what are your critical resources and how to optimize their usage, that is, often maximize their usage. For example, memory bandwidth is often a highly constrained and critical resource. Another way to think about things while you're approaching your design is how do you keep resources busy? If a resource is idle, it means you don't have quite as much efficiency as you would otherwise like. If you can keep everything busy all the time, well, it's like a car production line. Every step in the production line is doing something every minute. Your hardware design should have a similar feature to it, if at all possible, that everything in the design is doing something all the time. You should also be thinking about algorithmic optimizations to your design. For example, algorithms that avoid DRAM access since dynamic memories are slower than on-chip static memories. A classic example of this that's done all the time is to compress tables. So there's a compressed form on the SRAM that allows you to do most of the decision making related to that table in the SRAM before doing a slower off-chip DRAM access. There's also all sorts of algorithms that come from our computer scientist friends that can be useful here. Boyomorphic string matching, hash table for matches, and so on. In fact, it's actually quite useful for an ASIC designer to have taken a graduate or senior level computer science algorithms class, so you can start learning about these common algorithms that are out there that might be useful to you. While you're doing your design, you should be thinking hardware. That is this big? Is this small? Is this slow? Is this fast? For example, large finite state machines get slower as you add states. You might want to split them up into a hierarchy of state machines, as we talked about in the state machine notes. Be really careful about large units, for example, multipliers, even adders, and memories. I've given the example before of someone, this is an actual example from a student, of writing for I equals 1 to 1,000, A equals B plus C star B D, something of that essence. Essentially building 1,000 multipliers. Think a little bit about your fan out while you're designing your structures. How many other gates is a particular gate driving? If the fan out gets large, for example, you're driving 100 or 1,000 gates, then it could be slow. A minor issue, but it's still kind of relevant, it's avoiding priority logic when non-priority logic is sufficient. Remember the distinction is in the case statement. If you can reorder the cases in this case statement, then it's non-priority logic. However, don't get too carried away with this. If you need priority logic, implement it. It's not that big a difference. And of course, for your large units, there's different ways of implementing them that lead to different speed area trade-offs. For example, for arithmetic, a carry look-ahead adder instead of ripple carry. When you write plus in synthesis, you're getting a ripple carry adder. If you want a carry look-ahead adder, you have to design such or reuse someone else's design, which is the point we're getting to next. And that is to exploit existing intellectual property. So many of the synthesis vendors, whether you're using Synopsys for standard cells or using a FPGA design, often provide you with what's called intellectual property. This is other people's designs that someone's gone to a lot of effort to try to get fairly optimal. In Synopsys, this is called designware. It's a library of designs that includes many arithmetic functions, advanced math functions, and so on that you can call within your design. When you're using plus, minus, star, comparison, and so on, you're actually using designware and using it automatically. Remember again, here's plus gives you a ripple carry adder, as of course does minus. If you want to use other modules, including things like carry, look ahead adders, you have to implement them directly using using something like this example in order to get the function you want. So the example I'm giving here is actually using a cosine function from designware. The actual function is called down here. A sine cos out equals cosine of some angle. Above here, I've specified the wires that go to cosine. There's parameters associated with this function, so you can change the length of the inputs and outputs. Here I've included the code that gives the Verilog for this, so I can simulate this pre-synthesis. This is one example of how to use designware. If you want to use designware, I encourage you to explore this yourself. In our EDA resources, there is actually a small tutorial on how to use designware. So that brings us to the end of this particular submodule. I remind you, always design before coding, and always design the data path first. It reduces the complexity of tackling a complex design. Because after you design the data path, all the controller has to do is jiggle the control lines in the right sequence. It makes things easy. We talked about different styles of controllers. Counters, finite state machines are by far the most common. If you're pipelining the design, you might need to pipeline the finite state machine. This is essentially done by pipelining the state register. And while you're doing design, you have to think hardware. How do I maximize my use of critical resources? How do I keep my design small? How do I keep my logic use maximized and exploit the implicit parallelism of logic? And remember, reset goes to all the registers that specify the state of the machine. I now encourage you to do the internal quiz related to this submodule before proceeding to the next submodule, in which I'm going to show you how to apply these to a real-world design.